Welcome to the e-Pathshala lecture series in computer science, and this is a course in cloud computing. Today we will talk about the mechanisms of snapshot. So, the learning objectives of today's module will be, we will look at Chandy-Lampert's algorithm. Already we have seen the algorithm. In this module we will look at an example. We will see why snapshot is required with respect to an application or other applications that are useful in cloud. To be specific, we will look at one application which is checkpointing, that is extensively used in cloud, and we will also see the usages of checkpointing, followed by the summary. So, in the last class we saw the basic idea of what is a snapshot, and we looked at the snapshot in cloud, and we looked at the one basic algorithm, which is the Chandy-Lampert's algorithm. And this class we will continue with the discussion of Chandy-Lampert's algorithm with respect to an example. So, let us do a quick recap of what is snapshot. A snapshot is basically a set of pictures, pictures taken from various parts of one system, and at the same time. The important component of a snapshot is that if the system is spread over different locations, then we should take the picture of each location, but the time at which those pictures are taken must be the same. So, therefore, essentially it is what the name suggests, it is a photograph. So, a global snapshot will be a combination of all such snapshots that has been taken locally, and then put them together in one single snapshot, and that represents the system as a whole. So, when my system is spread all over the geographical locations, then to know what is the system, to understand where what the system is doing, or exactly what is happening in the system, we take a global snapshot. So, essentially taking a global snapshot is equivalent to global state of the system. So, if I take an exact global snapshot, then it is taking a global state of the system, which involves taking individual states of each process. So, if I assume that a distributed system is nothing but a combination of so many processes which are spread all over the globe, then we take the state of every process, as we have already said, at the same time. We must ensure that the snaps are taken at the same time. Plus, we have one more component, which are the channels. It is very important that we understand that with the distance across two processes, it is quite possible that some message, some important data are in transit, and these in transit data must be included in the global snapshot. Together, we have a global snapshot, which also represents the global state of the system. So, let us quickly look at what the Chandy-Lampert's algorithm was. So, the first step was that one of the processes will initiate, that is step 1. We change the color to red to indicate that the process has recorded its own state, and then this process will, in step 2, this process will send a specific special message called a marker message along all the outgoing channels, and in step 3 it starts recording all the incoming messages of the on all the incoming channels, and every time there is a marker that comes through an incoming channel, the process stops recording that channel's state and turns the color red after indicating that this channel is empty as far as this specific recording is concerned. The channel does not have to be empty in terms of physical messages. It can still have messages, or it can still be communicating messages through the channel, but as far as this recording is concerned, this channel will be considered as empty. On the other hand, if a process is not an initiator, then that process, how will that process record its state? It will wait for a marker to come through one of the incoming channels, and we will see shortly how every channel has to carry a marker through itself. And when a process receives a marker for the first time, so through all its incoming channels it will receive a marker, but for the first time when it receives it, it starts recording, it records its state, and it indicates that that particular channel to be empty, and then it follows the step 2, which is sending the marker along all its outgoing channels, and it follows step 3, which is that it records all the incoming channels. So, when all the components of the system becomes red, we know that the algorithm should be terminated or has come to a terminating state. So, now let us look at this what are the conditions that this algorithm requires. The first, that nothing fails. We assume that it is a fail-safe environment, a stable environment where nothing fails. So, when Chandy-Lamport algorithm starts, after that till the algorithm finishes, we assume that there are no components which fail. So, the communication is anyway reliable, and we have an exactly once protocol, and we assume that the processes do not fail. If a process fails, then we simply restart the algorithm. Now, the second condition or assumption, so to say, is that the channels are unidirectional. So, if P1 is sending messages to P2 and P2 is replying to P1, then we need 2 channels because they are unidirectional. A very important characteristic of this is that the channels are FIFO, first in, first out. So, if there are 2 messages going through the channel M1 followed by M2, then the delivery of these 2 messages will be M1 followed by M2. That is a requirement, and it can easily be done. We have looked at we saw in our communication module that making the messages be delivered in order is not a very difficult issue, and it can be easily done. The next condition is that a channel may be present, may or may not be present between any 2 processes. In case the process wants to communicate, a channel will be present, otherwise it may not be present. An initiator is a process that starts the global snapshot or the global state. Any one process, one of the participating processes will start, and that particular process is called the initiator. Any one of the processes can be the initiator, and the usual execution, normal message passing is not interrupted during the snapshot mechanism. So, snapshot will continue, but other messages also will continue being exchanged among the processes, and that is why that is the beauty of this specific algorithm, that it does not interfere while it is running, it does not interfere with the other workings of the process. So, the process can continue sending and receiving messages as well as doing all other executions. So, here is our example. In this example, we have 3 processes P1, P2 and P3, and we have 4 messages M1, M2, M3 and M4, and let us assume that P1 is the initiator and the initiation happens after it has sent M1. So, this is how we will represent the system. The 3 processes are represented by circles P1, P2 and P3, and these are our channels. There will be a total of 4 channels, P1 to P2, P1 to P3, P2 to P1 and P3 to P2. These are the 4 messages that are going to go and come, and we have to see how a global snapshot is taken using this system. So, first let us say that before initiation P1 sends a message M1. So, let us send P1 to P2 the message M1. In the meantime, P2 has also sent the message M2 to P1. Now, the point to note here is M1 has not yet been received by P2. Similarly, M2 has not yet been received by P1, they have been sent. So, they are in the channel somewhere on the way. At this point in time, after sending M1 and before receiving M2, P1 decides to record. So, what are the recording it has? If we look at this, it has, this is the recorded state at this point in time, where it says send message is only M1 and received message is null. So, it has not yet received any message, it has sent one message. Now, let us assume that after it has recorded its state, what will it do? According to Chandy-Lamport, it has to send a marker. Marker along what? A marker along all its outgoing channels. So, let us send, it has two outgoing channels P1, it has an outgoing channel, channel C12. So, it sends a marker along this channel to P2, and along channel 1-3 it sends a marker to P3. Now, let us assume that M1 will be received by P2. P2 does not know that marker is coming. So, P2 simply receives M1 and waits for the next message to come, and then it receives P1 receives M2. Now, since P1, we can see from this example that since P1 already has recorded its state, what does P1 do for all its incoming channels? It waits for a message to come and it records the message. That means, after P1 has recorded, when along channel C21 M2 came, it got included in the received part of the channel of the process P1. Now, it receives the P2 now receives the marker and P2 starts recording its state. So, P2 records the state as to what? It has sent a message M2 and it has received a message M1. This is P2's recording of state, current recording. And since P2 has received a marker along channel C12, it will also change the color of this channel to be red, indicating that the channel is empty as far as this specific recording is concerned. Now, let us see that it has to, now P2 has recorded its state. So, what it has to do? It has to send a marker along its outgoing channels. P2 has only one outgoing channel, it sends a marker along that. Now, what will happen? Assume that P3 is sending a message M3. So, M3 goes along the channel to C32 and assume that P1 sends a message M4. So, M4 goes along the channel. Now, if the marker M that has gone from P1 to P3 earlier when P1 has recorded its state is received by P3, what will P3 do? P3 will record its state. So, let P3 record its state. Now, in this recording, it says that it has sent M3, but it has not received any message yet. And then it will make the marker coming sending channel red, indicating that the channel is empty. Although we can see that M4 is still there in the channel, as far as P3 is concerned, it does not indicate any knowledge of having N4 because it has not yet received it. It can be anywhere. Now, let us assume that it receives, it sends a marker along the channel 3, channel 32 and then it receives M4. When it receives M4, what does P3 do? That is what Chandy-Lamport's algorithm decides. What should P3 do? P3 can either include M4 in the current state recording or can ignore, does not include and ignores as far as the recording is concerned. What P3 does is it does not include M4. Why? Because M4 has come only after the marker from P1. So, therefore, P1, if we look at the state of P1, P1 has not included a sending of M4. Therefore, the FIFO channel ensures that P3 also has not included M4 in its receive part, thereby making it correct. Now, let us look at what happens to when P1 receives this marker. P1 receives this marker and changes the color to be red, indicating that the marker has the channel is empty. Now, let us assume that M3 is received by P2. Now, since M3 has come before a marker, what will P2 do? P2 will include it in the received set. So, it will be received by P2 and be included in the set, and then P2 will take the message marker message M and will include and change the color. So, what happens at this point in time is that all the components of this of the system have been turned red, and therefore, we say that the algorithm has completed. So, when all the components become red, we say that that's a termination of the algorithm. What we do at that point in time is we collect all the local states of every process, and we say that this is our global snapshot, which is again equivalent to the global state. Here we did not look at the channels separately, as we indicated earlier on that a global snapshot or a global state is the state of each local machine plus the state of the channels. Instead of that, the Chandy-Lampo's algorithm very intelligently have included the channels messages, have made the channels messages be pushed inside the process. They force the process to receive the messages that are to be included in the recording, in a specific recording. So, the mechanism that has been added to this Chandy-Lampo's algorithm is that the channels are FIFO. So, when the channels are FIFO, then what happens is, it is like let us assume a small pipe, and let us assume a cricket ball is pushed through it. So, such that the pipe is such that only the one cricket ball can go. Then what will happen if I push one red ball and then one green ball and then one yellow one? Then what will happen? The red has to reach the other side first, followed by the green and then only the yellow. So, the order cannot change. That is the beauty of having a FIFO channel. So, Chandy-Lampo uses a FIFO channel and thereby ensures that all the messages that are recorded as sent by the sender will also be recorded as received by the receiver, thereby making a globally consistent environment. So, the algorithm creates a consistent global snapshot and therefore consistent global state. Very easily we can see that it is also a cut. What is a cut? A cut says that along in a timing diagram of a set of processes, a consistent cut is one where all the sends to the left of the cut, the corresponding receives also should be to the left of the cut. If a receive is to the left of the cut, the corresponding send has to be necessarily to the left of the cut. So, using logical clock, snapshot, Chandy-Lampo's algorithm creates a snapshot. So, here in our example, we see that the process was process P1 had initiated the global snapshot at this point after sending M1 and before receiving any message, and we see that the cut is in this way. So, the cut is here along the after M3 and before M4, the cut has been included. Now, let us look at the use of snapshot in cloud. There is something called a checkpointing, where perhaps the most important application of snapshot in checkpointing. We do deadlock detection. Deadlock becomes very expensive when such mechanisms, deadlock occurs in a distributed environment, and detecting it is important. So, deadlock detection can be done using snapshot, global snapshot. Many times process uses starts using some memory space or some other resource, and then it forgets to collect those garbages, but it terminates and goes. Finding that these garbages and clearing them, freeing them for the next user is the mechanism called garbage collection, and that can be done using snapshot. And last but not the least, when a computation is happening in many processors, we do not know whether the processor has terminated or not. So, termination detection of a specific computation is also a very important work, and we use snapshot for this. So, checkpointing, we will talk about only one of these applications, which is the checkpointing. There will be failures in a distributed environment. In any machine, there will be failures. So, and cloud is a cluster of computers. The more we add machines, the more is the probability of failure. So, therefore, in this, in spite of the failures, one of the major characteristic of cloud as put by Colleries is that it should be it should have the ability to recover from fault. So, failures are not cannot be stopped, but when this failure occurs, how quickly and how correctly we are able to recover from failure is what is an important criteria that we should keep. And checkpointing is such a mechanism which lets us recover from fault easily. So, what does it do? We keep on periodically, keep on saving the states of the machine periodically in stable storage, and then for every running application, if we do that, then if the machine fails, then when the machine comes back up, we have all the applications and their states in the stable storage. Therefore, we can recover to that particular state and restart from there. From this system can easily recover. If we have to save every application at regular intervals, these are called checkpoints, and save the checkpoint in stable storage. These saved files are called checkpoint file, and these files are our recovery mechanism. But the question comes is, how much to save, what to save? Do we save all the states? It becomes very expensive to be able to state all the states in a stable storage, and also saving takes time, and this is the time of the application running time. Therefore, when we save all the states, it not only becomes very expensive, it also reduces the overall performance. So, even though it is expensive, even though it reduces the performance, the importance of checkpointing is immense, and therefore, service providers will always go for saving the states, doing checkpointing. It provides availability, it allows program debugging, it helps a process to migrate, and it helps load balancing. So, what is availability? A task that is running for a long time should continue running as long as it wants and whenever it wants. So, regular checkpointing saves the states of these applications at well defined intervals. We do not want to save all the states, we want to save only some states. Anytime if the system fails, then we can go back to the last checkpoint and we can restart the process from that point. So, this way we can safeguard an application from restarting all over again. Profits, how cloud makes profit by checkpointing? Cloud says if you do not want the process to run all the time, then your process, your priority is less and you can pay less. So, certain services are given which are more expensive. Some CPUs to some other processes CPU cycles are given at a less priority. So, if a low priority process is running and if a higher priority process comes, then we have to withdraw the low priority process and run the high priority process. Therefore, the low priority process will be withdrawn perhaps many number of times, and if we restart these low priority processes from the beginning, it will be very expensive. Therefore, we create checkpoints for these low priority processes, and we withdraw a low priority process only back to the last checkpoint and restart these low priority processes from these points. So, from the customer side, if a customer does not have a deadline, if the job does not have to be completed within a certain time, it always makes business sense for the customers to opt for a low priority job. It takes longer, but it will be finished on certain time. The third point of importance of checkpointing is migration. A sudden spike in cloud is very common. If a sudden spike comes and we have to tell customers that we cannot serve, it is not good for the provider. So, therefore, some tasks will be chosen which does not have a security problem or such things, and it will be migrated to another data center or even to another cloud. Checkpointing again helps us to do this migration, because we go back to the last checkpoint and we migrate such jobs. The fourth point is the maintenance. If suddenly I need to do some kind of maintenance activity in cloud, then what we do is we stop all the processes running till the last checkpoint. Cloud will always be busy and there will be many processes that will continuously run. So, it is impossible to shut it down suddenly, but we can use checkpointing mechanism and we can do the maintenance. So, checkpoint is used for all these four purposes. The energy efficiency of checkpointing, if I have some server having which can run 100 processes, have only running half empty or very less, and therefore, what we can do is we can take all the processes of one of these servers and migrate them or shift them to another server and shut down the current server, thereby saving energy for the cloud service provider. So, many service energy saving mechanisms are available, but checkpointing is definitely a very important cloud. Now, what are the challenges? There are several challenges. The first one is to find a relationship between what happened in the past and at the time of failure I have to go back. So, there has to be a correlation between at what point in time a failure happens and what point in time it has to be checkpointing has to be restarted. A second challenge is minimizing the execution time. The farther we go, the more time it will take. If we want to make many checkpoints, again it will take more time. So, therefore, a lot of research has happened on what time is a suitable time to have the checkpoints, so that the expense is less, is the minimum. So, to conclude this module, we have seen that Chandy-Lamport's algorithm for taking a local, a global snapshot with all the local snapshots, how it is to be done using a through an example. We discussed the usages of snapshot in cloud. We saw that there are 4 usages, and all of them are important usages and should be continued, should be done continuously in a busy environment like a cloud service providers data centers. In that we saw checkpointing is the most important one, and the others are not less important, they are also very important. Deadlock detection can easily be done using a snapshot, and garbage collection and the mechanisms of all these are simple. In the next class, we will look at how concurrency is controlled in cloud. In cloud, there are various processes running together, and these will have a concurrent access to all the data and computation, and this concurrency creates inconsistency in our databases, and there have to be a very emphatic mechanism using which concurrencies have to be controlled. That is our topic in the next module. These are our references.